So what is real analysis? So if I go by the usual definition, it tells that in mathematics, the branch of real analysis studies the behaviors of real numbers, sequences and series of real numbers, and real functions. This is the technical definition, but to make things easy, real analysis is the mathematics of precision. That means it actually tells how calculus works, not just how you do the calculus. Further, if you see that it tells that real analysis is the branch of mathematics that gives you a kind of a logical and structural foundation of calculus. Also, you can say that calculus teaches you what to do, but real analysis teaches why it works. That means it ensures that every theorem, every mathematics, every equation in calculus stands on a logically unshakable base. So when we are doing calculus, or when you are doing calculus, you deal with differentiation, integration, and further calculations that are involved. But have you ever asked this question, that what really is a limit, or what exactly do we mean by continuity or infinity or concepts like that? So if you take from calculus, real analysis is actually building calculus from the ground up. That means you actually really now know that why calculus, the concepts of continuity or infinity or limit actually works. So from here what we can tell is that it answers in definitions that can be proved, tested and generalized. That means whatever the calculations or the theorems that you have done in calculus you have taken for granted, it is not like that. It will be much more foundational, much more tested, and what we can say is that calculus teaches you what to do, real analysis teaches you why it works. So that is in a way that you can understand what is real analysis before I go ahead and tell you about the books, procedures and methods of understanding. Now here is a quick and a very simple mathematical example which will make you understand the real power of real analysis rather than some vague English definitions. So for example, if I start with this example, as x gets closer and closer to 2, function of x gets closer and closer to 5. It means that if we plug in the values, for example, x equals to 2, the output comes somehow very near to 5. So for example, f of x equal to 2x plus 1, then this table actually shows that if x goes from 1.9 to 1.99 to 1.999, the value also comes closer to 4.98, 4.998 and so on. So here you can see that as x moves nearer and nearer to 2, function of x moves closer and closer to 5. So in definition, in terms of calculus, we write like this: limit of x tending towards 2, f of x equals to 5. Now this is a fairly intuitive idea. Based on the numbers, we get the formula, we plug in and we score good amount of scores in our calculus examination. But what does closer and closer actually mean? Now this is where real analysis actually comes in play. How close is close enough? Is 4.9 close to 5? Or what about 4.99999 close to 5? So we need a mathematical way to describe what do we mean by closeness, or something very closer and closer, what do we mean? And in order to do that, mathematicians and physicists have involved two concepts which are called epsilon and delta. Now I would like to give you a very simple example and translate these two Greek symbols, epsilon and delta, and tell you what actually it means. So when we talk of epsilon, we means that how close we want the output, or for example to be the limit of, say for example, L. That means I can tell that you can think of epsilon as our tolerance in the y direction. So if I want, for example, function of x to be within plus minus epsilon, that is the tolerance of L, then we can tell this is the value of the epsilon. Now what is delta? Delta is how close the input x must be to A to make that happen. So that means that think of delta as the tolerance in the x direction, and in simple language we can say if x is within plus minus delta range of A, then function of x will be within plus minus epsilon of L. So this is basically what we mean by epsilon and delta. So epsilon is, I will come to summarize that part, but here is a step-by-step idea. You decide how close you want of the function of x to be to the limit of L. For example, within 0.1 or 0.001 or 0.00001. So that is basically the epsilon. So how close you want to be. And then you ask this question, how close must x to be to a so that the function of x f of x stays close to L, and that is what is your delta. So from here we can summarize that if such a delta exists for every epsilon, we say the limit exists and equals to L, for example the epsilon. So the delta definition makes the idea of limits precise, as you can see. It means for every small error, for example epsilon, you allow in the output, you can find a small distance delta around the input so that the function stays within that error. So simply taking, you can say that if such a delta exists for every epsilon, the limit actually truly exists, and this is how real analysis brings the exactness to our intuitive calculus ideas. So that is how things actually starts into play. So here you can see actually how do we defining epsilon as I want to be close within that range, and delta, if x is within that plus minus delta range, then a function of x will be plus minus of epsilon of L. So from here we can say that real analysis actually it is making our intuitive ideas of calculus much more precise, foundational and continuous or tending to infinity. These are now rigorously presented in terms of the language of epsilon and delta. So that is why we introduce those concepts. Now, if I want to further test, for example, if I want to test this with function of x equals 2x and a equals to 3, we will claim this one. Now, is this true? Let us say, for example, so if we start with this condition which is less than epsilon and we substitute just simply function of x equals to 2x, we get this value. And from here we can, what we can do, if we divide both sides by 2, we get a value of this. So if we select delta equals to epsilon upon 2, then whenever we get this value, we get something which is less than epsilon. And from here what we can deduce is that for every epsilon we can find a delta, that is the limit actually works perfectly. And further what we can say is that as x goes near 3, 2x goes near 6, and this is actually precisely written in this definition. Now this is a set theory definition. I will explain you what this means. So first of all, what does this inverted a means? Inverted a epsilon greater than 0. It means that for every epsilon greater than 0. So no matter how small a distance you are selecting, no matter you choose around the value of L, in this case for example 6, you can handle it. So inverted is basically a universal quantifier in terms of logic, but here it means that for every epsilon greater than 0. So this is actually what it means. So if I say, for example, if I want f of x to stay within 0.0001 of x and so on. Now if I take the second one, which is an inverted e delta greater than 0, that means it is again a mathematical term. It tells there exists delta greater than 0. That means if I can find a matching small distance delta for x so that this actually happens. So you can again say delta is like your input tolerance, how close x must be within the target point of 3. The next part, again, it is a set theory such that if means actually x is close to 3 but not exactly equal to 3. That means you're looking at points near 3 nor not right on the top of it. Then 2x minus 6 is less than epsilon. That means the output value 2x will be close to 6 within your tolerance. That means that if I take this kind of an pictorial understanding, then no matter how tiny a band, for example epsilon, you draw around the number 6, I can still find a band around 3 so that whenever x stays within delta to 3, 2x will also stay within epsilon of 6. Now if I go back, here you will now see that this definition is clear. For every epsilon greater than 0, there exists a delta which is greater than 0 such that so and so the conditions. So I explained you those set theories in simple English so that you can understand. So 2x minus 6 less than equals to less than epsilon means that how small a band, for example epsilon, you put around 6, you can still find a band delta around 3, so that whenever x stays within that delta of 3, 2x also stays within epsilon of 6. So from here what you can tell simply is that epsilon means how close do I want to get to the answer, and delta means how close do I need to be the input to make that happen. So as x moves close to 3, function of x moves closer to 6, perfectly controlled by epsilon and delta. That actually confirms the notation that x tending towards 0 to x equals to 6 with precision. So this is basically, I would say, in a way, how we are actually defining closely the value of limit and near and close and so. So that is how real analysis actually transforms the word approach or approaching into a kind of a proof. The question remains that in spite of all those understandings, is there any practical implication? Because I have seen most of the students telling that real analysis is a very dry subject. It is based on pure mathematics. It has got hardly any application. So why should we learn it? Definitely, at the first go, real analysis looks just like complicated symbols. But it would ask you, or you can ask yourself this question, why actually calculus works? That means if you're learning calculus, you learn how to differentiate, how to integrate, how to find limits. But real analysis gives answer what exactly is the limit. When does function really have a derivative? Or why does this formula works in this way and that way, and why they do not fail? So calculus and real analysis in some way are all related to quantum mechanics and quantum physics, which are related to continuity and convergence. So real analysis is what makes those ideas. You can take an analogy telling that if calculus is basically driving the car, then real analysis is basically the engine. It tells how the car actually works. Now from here I can tell that real analysis is closely related to physics, because real analysis provides a rigorous foundation for understanding continuous change in space and time, which is essential for solving physics laws. It is also related to engineering because it ensures precision in modeling signals, systems, optimization problems where accurate limits and convergence determine stability and performance. Also in computer science, it underlies algorithms for numerical computations. Machine learning graphics guaranteeing their continuous process can be approximated and analyzed effectively. So remember that it is absolutely not a useless abstraction. It is the grammar of mathematics. So for example, if you know the grammar well, you can pick up any language easily. So real analysis actually tells you how to calculate. So if it is a comparison without real analysis, it is just a formula. You accept that it is infinite. You just draw curves. But with reanalysis, you prove when they work, you know how to test convergence rigorously, and you can define continuity and limit and smoothness, actually what they mean. So this actually gives you an understanding the power, the real usage, and in terms of using real analysis really. So practically, if someone wants to go beyond applying formulas, then you need to understand real analysis. Also, real analysis is something which builds your mathematical muscle. Why? Because it trains your brain in a rigorous logical thinking, which you have not done in calculus. You have just assumed and you have plugged in the formula and you got the results. So writing proofs actually improves structured argumentation. You can understand these concepts, and logical rigor sharpens your analytical reasoning, coding, and policy modeling. So all in all, what we can see is that real analysis is what ensures that the mathematics we use in science, technology, economics, or whatsoever works reliably, precisely, as well as predictably. We move to the next part, which is what are the mathematical prerequisites required for mathematics. Well, you need to know what are called algebra and inequalities, because you should be comfortable with these kind of expressions which you can see right on the screen, because reanalysis constantly deals with absolute values, inequalities, etc. You should be aware what this mean by less than epsilon, etc. The second point is functions. You need to know functions and graphs, because without that you won't be able to understand what is a domain and range, inverse function, composition of functions, and so on. So in real analysis you need to study properties of functions, continuity, monotonicity, boundness, all these things. So a very good understanding of functions and graphs would be the second prerequisite. Third would be obviously basic set theory, because the entire part of notations are written in set theory. So union, intersection, quantifiers, all these things would be required, because real analysis is written in the language of logic. So this type of statement which I have just shown you should be familiar with. Yes, sequences and series from calculus should be clear, because you need to know what do we mean by sequence, when does it converge, etc. Why? Because much of real analysis starts with what do we mean by convergence, numbers, sequences, and so on. And the fifth would be coordinate geometry, because that is something which is very intuitive: slope, derivative, area under the curve, and these are required because this would come intuitively for formal proofs, so that you do not feel it dry. Mathematical proofs and reasoning, I have already made a video on the sheer importance why you should have an understanding of mathematical proofs. It is important. This won't come in a day, so you have to really practice, because reanalysis is completely a proof based subject. Each theorem, each equation, you need to go ahead and prove it, and that is why from calculus you move to reanalysis. You prove those theorems and understand the power and the beauty of that. So coming to the main core idea of this today's video, what is the best book to start for reanalysis? There are many books in Amazon and if you search in Google, but I would recommend this book by Shanti Narayan and Rain Singhania, that is Elements of Real Analysis. You can quickly pause and take a look of these Amazon reviews. All of these reviews are telling excellent book. It is so good that even layman can understand, and this is the best book of reanalysis in the universe, written by great mathematicians, Sir Shanti Narayan. So overall, I also feel that this is one of the best book to start with, and I will give you the reason for that. Now, before I go ahead, I will just tell you how the book is arranged, and not only how the book is arranged, I would say this is the best and the perfect sequence in which your understanding of real analysis should start with. First, sets and functions. This is the language of mathematics. So the book actually starts with giving you an idea of sets, statements, and function, because this is the grammar. So here you can see I've just taken screenshots of few of the what do we mean by set, functions, etc. So you go ahead and understand what is a composite function, inverse functions, and binary operators, symbols like this. All of real analysis, continuity, limits, differentiation are properties of function. So the first chapter actually builds the language of symbols, and you need to understand that. This is a screenshot of 1.1 to 1.9. Page numbers I have not given. These are this is quite a dense book, I think around 600 plus pages. So these are sets and functions, statement, connectives, etc. First step, and this is the way you should also continue learning. The second would be real numbers, obviously how you build up the number system. So the book actually goes ahead and tell you how to construct the real numbers are, and you already know that square root of 2 is something like that, and it is an irrational number. It cannot be expressed in this term. So in order to express those things, we need to have new set of numbers which fills up the gaps, and that is what the real numbers do. They make the number line continuous and complete. So the concept of boundedness, supremum, infimum, all those things come in play, and this is the second most important step. Now, why it matters? The reason is that completeness of the real number ensures that every Cauchy sequence actually converts to a real number. I'm not explaining, this is a technical part, but this is the backbone of real analysis. How we build the construct, how we construct the real number lines, that is important. And here you can see a very exhaustive contents given in terms of understanding real analysis or the real numbers, starting from introduction to objective question. This is step number 2. Third step comes once you know what is the real number line, you go ahead and understand neighborhoods and limit points. So the idea of closeness in calculus is now being rigorously explored. So you need to understand, for example, if I take this kind of a simple example, a neighborhood point of A equals to 3. So if it is 0.1, the neighborhood is between 2.9 and 3.1 and so on. So why it matters? Because these ideas define continuity property, this definition, and the limit itself is defined by this. So that is why you see all these symbols etc. will come in play, and you need to go first chapter. If you don't understand the symbols of set theory, you won't be able to proceed that. So this actually means that by taking x close enough to A, we make function of x as close as we want to function of A. This very simple mathematical language. So this is again the heart of real analysis. Again, you can see a very exhaustive table of contents. Screenshot I have given from Shanti Narayan's book. Neighborhoods, limits, illustration, closed sets, everything covered in details. After that comes a very interesting chapter and our fourth or fifth step in understanding, that is called countability of sets, where it actually tells that some infinities are bigger than others, and it explores finite, countable, infinite, etc. So for example, if I take set of natural numbers n equals to 1, 2, 3, dot, 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 so on, then we say it is countably infinite. We can list them in order. So the set of real number is uncountable. That means you can list all real numbers. You cannot list all real numbers which lies between 0 and 1. And that brings us to the famous Cantor's paradise, the famous mathematician George Cantor. This is the Cantor argument, shows that between 0 and 1, no matter how you list the decimals, one number will always be left out. This is being explained in the book. So real numbers are actually much denser than rational numbers, and there are infinitely many rationals between any two reals, but still the reals form a bigger infinity. So 0.1, 0.11, 0.1 and infinitely more exists. So here the book actually prepares you for studying the next step, which are called the continuity and limits. And here I have given again a screenshot of what is covered in terms of countability of sets. And then, as I have shown you, if you turn the page over here, this is actually a precursor to continuity and limits, and the next chapter talks about sequences, the foundations of limit and continuity. So you know what is the sequences A1, A2 and A3. So real analysis actually studies, it asks this question: as the index n becomes very large, does the sequence at all approach a limit? So for that we have different kinds of convergent sequence, it settles down the single value; divergent sequence, it grows without bound, and so on. A sequence where terms get closer to each other is called a Cauchy sequence. And then we have got monotonic sequence, which increases towards 1. So overall, sequence is definitely a backbone of analysis. They define limits, continuity, even integrals. And this chapter actually teaches you how to test, most importantly, prove and reason about convergence. So the sequences are this: sequence, bounded limits. Again, this is the next step, building the complete understanding of this sequence. Then comes what are called infinite series with positive and negative terms. So here the book again takes a big step, that is infinite summation. You know what is an infinite series look like. So from here we ask this question: does this infinite sum approach a finite number? And then again there are simple examples like each term gets smaller and the total approaches 2. This grows without bound, that is the harmonic series. Then the D'Alembert ratio test, the series converges, and so on. So series are everywhere in mathematics that we find. I mean to say, this is undoubtedly very important, and understanding why a series converges or diverges gives a analytical control, and you can understand the infinite process. Here again you can see quite a detailed, exhaustive understanding of infinite series is given in this book. So if I continue telling about these chapters, this video is going to be very long, and I'm sure will be getting bored and you won't listen to that. So to summarize the rest of the part, here are all the different parts of the table of contents. It's a very exhaustive book, and it gives you a complete understanding of how to go ahead with the understanding of real analysis. So you can handle now infinity and finally the abstraction generalization. So together I would say these are the table of content. This is a sequence in which you can go ahead to understand limits, continuity, and the underlying structure of mathematics. So if I give you a very honest book review of the elements of real analysis, then what I would say is that it is a amazing book. It has got a very good logical progression because it builds up right from the base, giving an understanding of set theory, logic, symbols, everything. And there is a huge amount of clarity given. Most importantly, what I have forgot to mention over here is that the book contains a huge amount of examples which you can solve and make your foundation better. So strong foundational emphasis on real numbers, etc. And it has got a wide coverage from limits to the advanced topics like metric spaces and so on. And if I talk of the my honest opinion about this book, then I would say it is strictly authentic and a disciplined introduction. It doesn't aim to impress you with shortcuts. It builds you from the base, so you start thinking mathematically. And if you approach it with patience, then you will see that the book actually transforms your way of understanding from logical system on limits, convergence, and completeness. It is built for layman, provided you have got a good understanding of set theory and other basic mathematics and elements of real analysis. Undoubtedly, it is a mathematical discipline of best form. Written, go ahead, pick up this book. Not very costly. You can find it, I think, online, or you can just purchase it. You can go ahead and start understanding about real analysis, and you won't feel bored. It's one of the best beauty of mathematics that I have ever found. So that's all for today's video. Thank you very much for taking up your time and watching. If you have liked this video, please do not forget to subscribe to my channel Physics for Students and click and keep the bell icon ringing, because there are a lot of interesting stuffs coming up. Follow me on my Facebook handles, Instagram, social media, and others, and you can write to me at this email ID where I will try to answer all your questions and queries at the best. Physics for Students will be soon back with a lot of interesting and fun-loving videos. See you soon, but till then, may the good Lord be with you.